Okay, for most people, when you implement a Lisp, linked list, they're obvious. So what would you implement? Something so ingrained into Lisp as arrays. After all, linked lists are the bread and butter of Lisp. Since Lisp was invented by McCarthy, linked lists were always part of the language. Most of the basic instructions, CDR, car, were created with the idea of linked list in mind. So why would you replace linked list with something else? If you ask a seasoned Lispian, arrays are not, the kind of stuff you want to see in Lisp. Arrays are for, lower level languages such as Python, Java, or C++. Not Lisp. Arrays still are much more efficient than linked list. This is the sad truth. They're more efficient when you want to insert an element, when you want to delete an element, when you want to access an element at a certain position. With an array, all you have to do is to provide the system with the index of the element you're looking for, and that's it. And they're also much more efficient to copy. Why? Well, with linked list, you jump all over memory every time you traverse a list. Why? Because in fact, each element is an object in itself. And each of these elements can be scattered all over the place. When you create the different elements that you're going to gather into one list, well, they could be created at very different places in memory. And to jump from one slot in memory to another is very costly. It doesn't come cheap. With an array, well, memory can be contiguous. And modern processors love contiguous memory because they have a lot of basic instructions to move one chunk of memory from one place to another. And because of that, when you insert an element in the middle of an array, it can be much faster than in a linked list. Because in a linked list, you have to move throughout memory to go from one place to another. And these can be quite costly. In an array, well, you go to the element through its index, and then you move a chunk of elements to the left or to the right. And when you move those elements, you're using very basic functions, instructions of your processor. And it's very, very fast. I know it's counterintuitive, but using arrays can give you an edge when you implement a language like Lisp. Right, but then in that case, implementing a CDR can be quite costly, no? Well, not exactly. So the way arrays are implemented in LispE actually, is quite straightforward. If you have an array, then what you build is what we call in computer science an indirection. So you have an object that contains a pointer to that array associated with an offset. And this offset, which I call home in this case, tells you where the first element of that array is. So of course, when you create this array the very first time, this offset would be 0. But if you do a CDR, then all you have to do is to create these very small objects, which is just a pointer and an offset, and to tell the system, well, this offset is set to 1. And because this offset is set to 1, and what will happen is that next time you try to access an element, well, this offset would be added to your index. And of course, it would be exactly as if the first element of your list is the second element of that array. And if you have an array, well, you can do APL stuff. Let's dive in, as ChatGPT says. So let's launch LispE. I want to present first to you a few of the instructions that I implemented on top of this array system that I used for lists in LispE. So the first instruction is iota. Iota is directly inspired from APL, what it does is very simple. So if I give a value, then IOTA will generate a list from 1 to 10 to 19 in this case. Okay, there's also a second one, which is IOTA 0, and in this case, instead of generating from 1 to 19 as it was the case here, we can generate from 0 to 9. And also IOTA can generate, a list of lists. So for instance, if I say list 5, then 6, then 7, then IOTA is going to generate, a list of 3 sublists, each counting to the number that was provided as an argument to IOTA. But we have, of course, some more interesting instructions, such as row. Row is certainly the most powerful instructions, and I use it all the time. It's a way to define matrices or tensors by giving, as arguments the shape of the list you're going to create. So let's say that I want to create a list that would contains 2 elements of 2 sublists of 3 elements each. And the system is going to generate a list that would, a matrix that would contain 6 different values. So I'm going to provide those 6 values. And that's it. As you can see, the system created a list of 2 sublists, each containing 3 elements. And what it did was to rotate among the list that I provided as a final argument. So if I do something a little bit different, for instance, if I say I want, as an argument, a list containing only 2 elements, what will happen is that the system will simply rotate among those values to populate the different sublists. And what is quite interesting is that if I store this list in a variable, let's say this one. So R contains the new sublist. But if I ask what is the type of R, what I can see is that it's a matrix of integers. And what is quite interesting is that if I replace these with one more dimension, then R is, of course, once again, going to count among the different elements twice in this case because of the last argument. So we have a tensor that contains 12 different elements and different sublists. So 2 major sublists, and each of these sublists contain 3 sublists of 2 elements each. And now if I ask what is the type of R, the system will tell me that it's a tensor. Okay, so what you have to understand is that these instructions are very important in the sense that to know that it's a tensor means that in fact what will happen is that when the system is going to multiply or add those values together, it will benefit from some of the most important instructions in a modern processor, such as SMID instructions, for instance, that would compute in a very fast way those multiplications or the additions. Of course, row can also be used to return the shape of a given matrices or of a given tensor, as it is the case here. We're going now to talk about the outer product. So here is an example. So what you have here is so the degree sign at the beginning of the expression is the sign that introduces this outer product, and then we provide an operator, and then we provide 2 lists. And what the system is going to do is to multiply those lists, each element of those lists together. So as we can see here, what happened is that we multiply 2 with 1, this is 2 here, but then 2 with 2, which is 4, then 2 with 3, which is 6, and 2 with 4, which is 8. And then we took this following element, 3 by 1 is 3, 3 with 2 is 6, 3 with 3 is 9, and 3 with 4 is 12. And the last computation is 4 by 1 is 4, 4 by 2 is 8, and so on and so forth. And so this is a way to distribute an operation among different elements from 2 lists. The other element I wanted to talk about is the inner operator. And so the inner operator is a little bit different. For instance, here is how you can use it to implement the multiplication of two matrices. So how does it work? So here, what this operator is going to do is to distribute these different operators among the different values in our two matrices. You can see that here we have a list of two elements, and here we have a list, 1, 2, it's two elements, and here we have two elements, a list of two elements. And so this size is compatible with this size. And so what we're going to do is simply to do the following. We're going first to multiply the elements together. So 1 with 6 plus 2 with 7. So 1 with 6 is 6, 2 times 7 is 14, which is 20. And then we're going to take the next element, 1 with 2, which is 2, and 2 with 0, and the sum is 2. And then 1 with 3, which is 3, plus 2 times 2, which is 5. And then 1 with 4 plus 10 times 8, which is 16, and the total is 20. And then we take the next element here, so 5 times 6 is 30, plus 4 times 7, which is 28, and the total is 58, and so on and so forth. So as you can see, those different operators can be quite handy, and I use them quite a lot because in fact there are many cases where I want to be able to generate exactly the kind of structure I'm looking for. And there are all other operators, but I'm not going to present them here. I will put the link to the description, to the documentation in the description, so if you're more interested you can read it. Thank you for watching and have a nice day.